Hi. Yeah, so I'm Sheron Look. I'm Amanda Spivak's graduate student, and I'm here to share the field data that we collected in Great Barnstable Marsh. These are, as people would say, hot off the press. So these are preliminary results, and I'm really excited to share this data with you today. So I'm sure you all are well versed in the ecosystem services that these wonderfully intricate ecosystems provide to human populations. But just to reiterate, we have services like storm surge buffering to carbon storage. Really, salt marshes play a critical role in the resilience of coastal communities to a changing climate. Yet, because these ecosystems are at the direct interface between human populations and the ocean, we have altered these systems to support human populations and our economies. And so one of the most extensive management actions in New England are the installation of parallel grid ditches during the 1920s and 40s. So the intention of ditching, as we've said before, involves the physical removal of sediment in these long parallel ditches you see to the left. And that was to provide employment opportunities during the Great Depression, as well as controlling mosquito populations that would breed on standing pools of water on the high marsh. Yet the long-term effects of these ditches on ecosystem functioning remain unclear. From aerial footage and digital elevation models from LIDAR, which stand for light detection and ranging, we know that ditches do indeed lead to the lower density of ponds on the ditch side through the drainage and reestablishment of emergent grasses within ponds. However, ditching may reduce ecosystem resilience to future sea level rise due to observed lower elevations in the ditch side compared to the natural side. Therefore, the question we want to answer are what the net impacts of ditching are on marsh sustainability and carbon storage in order to help resource managers make decisions that optimize marsh resilience and ecosystem services, such as carbon storage. So our experimental design involved selecting 3 transects in the white lines on the ditched and separately on the unditched side within Great Barnstable Marsh. And we took cores at 0 meters from the tidal creek, which we have labeled near channel, to 100 meters away from the tidal creek, so the marsh interior. And this will really help us evaluate the role of the tidal creek on the delivery of salt marsh ecosystem services, such as carbon storage. So in the field, we characterize plant characteristics like percent cover, plant height, and biomass, and also placed wells within the marsh to obtain water level data within the marsh platform. We also carried out extensive analysis on the sediment cores we collected, and to compare how ecosystem service of carbon storage differed between the ditched and unditched marsh, we needed to first carry out elemental analysis on the bulk or total sediment. Our USGS collaborators are then using lead-210 age models to determine the rate of elevation gain there is in the salt marsh platform to really understand why we're seeing elevation differences in the marsh. Finally, my favorite technique is ramp pyrolysis oxidation, or RPO, which allows us to understand the sources, age, and thermal reactivity of the soil organic carbon. And so with that, let's take a look at our results. So first, we'll look at how ditches have changed marsh hydrology. Our collaborators at USGS placed wells within specific locations of the ditched salt marsh, one at the creek bank edge in red, another at the ditch edge, green, and a third well in the marsh interior in blue. What we have plotted here is a section of the water level data in which the y-axis represents water level depth and time on the x-axis. On the furthest left section, left section of the x-axis, we have an event where water is overtopping the marsh. And with time, the marsh platform drains back into the tidal creek, corresponding with a drop in the water level within the marsh platform. And this happens in 3 repeated events here. What we observe here are that wells placed near the tidal creek, green, and ditches in red, drain at a similar rate indicated by the overlapping lines, and that the marsh interior is draining at a slower rate and maintaining a higher water level depth compared to the tidal creek edge and ditched edge site. So ditches appear to be mimicking the role of the tidal creek and effectively draining the salt marsh at Great Barnstable Marsh. So now that we're seeing how the ditches are effective in draining the marsh platform and affecting marsh hydrology, let's see how it changes the salt marsh ecosystem. So this first graph demonstrates elevation differences between the ditched in orange and unditched marsh in gray. The x-axis is distance from the creek bank edge from 0 meters to 100 meters, with this little cartoon at the bottom showing you how the 0 meters is the closest to the edge of the platform and 100 meters is moving towards the interior of the marsh. And then we have the y-axis is elevation with respect to North American vertical datum of 1988 or NAVD 88, which allows us to compare elevations across locations. So the points are mean elevation with the associated standard error, which allow us to see whether the data are distinct from one another. So at the 0 meter location closest to the creek bank, there doesn't appear to be a significant difference between the ditched and unditched side of the marsh. Moving towards the interior of the salt marsh, we observe differences between the ditched at lower elevations and unditched marsh located at higher elevations. So this really does support that LiDAR map we saw earlier with Amanda, demonstrating those elevation differences between the ditched and unditched side of the marsh. So we then measured percent cover of different salt marsh vegetation species in the field and plotted our data by taking the mean and standard error of the unditched and ditched marsh near the channel in the darker color and towards the marsh interior in the lighter color. We found that Spartina alterniflora dominated the marsh platform alongside Spartina patens that had distinct changes in percent cover, decreasing from the near channel to marsh interior for both the ditched and unditched marsh. So we know our dominant plant species is Spartina alterniflora within our marsh. We then wanted to look to how this might change our bulk soil properties. Firstly, we once again are comparing the unditched and ditched marsh separated by the near channel site in the darker black and orange and the marsh interior in the lighter color. And we find that overall, there are similar dry bulk density values between the ditched and unditched marsh, but there are these distinct differences within both from the near channel to marsh interior. And so this makes sense considering that we'd expect the deposition of high bulk density inorganic material from the tidal creek, resulting in higher dry bulk density values at the near channel location. So the similarity between the ditched and unditched marsh in terms of dry bulk density also indicates that compaction of the marsh soils doesn't appear to explain the difference in elevation between the ditched and unditched marsh, because the compaction we would expect higher dry bulk density values on the ditch side of the marsh. So while dry bulk densities were generally similar between the ditched and unditched marsh, we found that total organic carbon content in both percent and density were higher within the ditched marsh in orange. Additionally, we're seeing an increasing trend in TOC content moving from the near channel to marsh interior. Next, we move on to our lead-210 age models, which provide the year of sediment deposition within Great Barnstable Marsh. On my y-axis, I have plotted mean elevation gained in meters since 1920 with associated standard errors. And on my x-axis, years spanning from 1920 to 2018. I once again have separated out the ditched and unditched by near channel in the solid line, with the marsh interior in the dashed line. And while the unditched marsh and the ditched near channel marsh have been gaining elevation at the same rate, we see a divergence in elevation gain for the ditched marsh interior in that orange dashed line since around the 1950s. And so this would explain the lower elevations on the ditch side, and it's really amazing to see this distinct divergence in elevation gain around the time of ditch implementation. And just as a sanity check, going back to our bar plots, I've plotted mean accretion rates with standard errors on the y-axis in millimeters per year. And while the accretion rates are similar for the unditched marsh and ditched near channel site in that darker orange, we do see distinctly lower ditched marsh interior accretion rates in that lighter orange bar. So we're seeing lower elevation gain on the ditched interior marsh, but higher total organic carbon content values for the ditched marsh overall. How does this affect carbon accumulation rates within the Great Barnstable Marsh? So we have plotted here our mean carbon accumulation rates on the y-axis for the ditched and unditched marsh. And what we're seeing is largely similar but variable carbon accumulation rates within the unditched and ditched marsh. So this appears to demonstrate that the relatively higher TOC content is balanced by the slower rates of elevation gain within the ditched marsh interior. So this is my bread and butter. We then wanted to look deeper into where the organic carbon was coming from in Great Barnstable Marsh. Are we seeing different sources of carbon for the ditched and unditched marsh? So we focused firstly on the surface marsh horizons and plotted the mean del 13C values. And often we use del 13C to identify different sources of organic matter based on the ranges provided in the table on the top right. What we found was that the del 13C values reflected that the soil organic carbon was mainly sourced from salt marsh organic matter rather than the much more depleted marine and terrestrial organic matter. Ramp pyrolysis oxidation helps us better understand the sources, age, and reactivity of the buried soil organic carbon. And so this technique involves heating sediments from room temperature to 1,000 degrees Celsius on my x-axis and measuring the carbon dioxide evolved on the y-axis. And with this technique, we can quantify the amount of carbon dioxide evolved within the more thermally reactive peak compared to the more thermally stable peak and measure its carbon isotopic value to obtain the sources and age of these different pools of organic carbon. So here I've plotted the average thermograms with shaded standard errors for the unditched and ditched marsh surface horizon, with the x-axis being increasing temperature and the y-axis being the amount of carbon dioxide evolved at each temperature point. Both the unditched and ditched marsh have a similar bimodal thermal degradation pattern in which we see a low and high temperature peak, demonstrating similar ranges in thermal reactivity of the buried soil organic carbon within the unditched and ditched marsh. I've overlaid our thermograms with the percent of total organic carbon on the second axis to the right that constituted the low and high temperature peak. This low temperature peak, characterized with thermally reactive organic carbon that burns off at lower temperatures, constituted around 70% of the total organic carbon within the surface ditched and unditched marsh horizons. And the other 30% attributed to this more thermally stable component of soil organic carbon. And we've just received our radiocarbon analysis of these fractions of carbon dioxide we collected within these temperature intervals of the thermally reactive and stable peaks. And while the low temperature peak was characterized largely with young salt marsh organic matter, the second more thermally stable peak had contributions of radiocarbon old material, which I've characterized as older than 100 years old in radiocarbon age. Which is really old for being buried on the surface of the salt marsh platform. So this old material constituted most of the second peak within the unditched marsh surface, while the second peak within the ditched marsh surface had around 30% contribution of this old soil organic carbon. So this indicates contributions of organic carbon with 13C values of salt marsh organic matter that are older than modern, suggesting contributions of old carbon either from microbial recycling and or the nearby eroding marsh creek bank. So this suggests that one, we have contributions of old marsh-like material to the marsh surface. And secondly, we have, there may be these different contributions within the unditched and ditched marsh. So if the surface horizon consisted of this potentially older material, this would suggest an overestimation of carbon burial based simply on accretion rates and bulk soil organic carbon values, which is really what I'm going to be digging into in my thesis. So we've looked at the data for the ditched and unditched marsh, but we know that ditching was carried out to drain ponds on the marsh platform where mosquitoes would breed. So what happened to the ponds on the ditch side of the marsh and how exactly did they recover? So when you're standing on the ditch side of the marsh, you can't really tell that there were previously ponds on this marsh platform simply looking at vegetation or elevation. Yet, if you look in aerial footage taken by USGS in 1938, there were previously ponds on the ditch side of the marsh. And so we selected 6 sites in the marsh that showed evidence in aerial footage of ponding and compared them to the surrounding marsh that had not experienced historical ponding. Additionally, these ponds resided at differing distances from the tidal creek to evaluate the potentially important role of tidal creek flushing and its contributions of suspended sediments to marsh elevation gain and pond recovery. So first, we once again looked to our plant characteristics. We wanted to see whether the plant communities within the infilled pond were similar to that of the surrounding marsh. So the dominant plant species in both the infilled pond and ditched marsh were Spartina alterniflora. And on my y-axis, I have the mean and associated standard errors of plant height in centimeters and biomass per unit area for the marsh in black and infilled pond in green. And here we can see that infilled ponds actually had greater plant heights and biomass per unit area than the surrounding salt marsh. Well, if we're observing higher plant heights within the infilled pond, we then wanted to determine whether these ponds had recovered to similar elevations as the surrounding marsh. On the y-axis, we have elevation based on NAVD 88, going from high to low elevation, and my x-axis is distance from the tidal creek from 0 to 100 meters away. We made duplicate observations in the ponds in green and marsh in black. And generally, we observed slightly lower elevations in the infilled ponds compared to the adjacent marsh at similar distances from the tidal creek, suggesting that infilled ponds are still recovering in elevation to the surrounding salt marsh. So then we used our lead-210H dating within the marsh and infilled ponds to obtain those sediment accretion rates. Firstly, this plot shows mean accretion rates on the y-axis for the marsh and infilled ponds. And we find that the marsh is keeping pace with current relative sea level rise of around 2.8 millimeters per year in Great Barnstable Marsh. Secondly, the infilled pond in green is accreting at nearly double the rate of the surrounding marsh. To emphasize how crazy this elevation gain is, I plotted on the y-axis elevation gains since 1960 in meters for the marsh in black and infilled pond in green, and that the infilled pond gained elevation more than half a meter over the past 5 decades. This demonstrates how our recovered ponds, characterized with greater plant height and biomass, accreted at a fast pace to nearly recover to the elevation of the surrounding marsh. So in conclusion, there are a lot of complicated processes happening on the marsh that have been affected by ditching, and we're still processing that data. We know that ditching mimics the tidal creek in its role in draining the salt marsh. We observed that the ditched interior marsh resided at a lower elevation, which was explained by the slow elevation gain since the 1950s. The ditched marsh, interestingly, had higher total organic carbon content, but the slow elevation gain resulted in generally similar carbon accumulation rates with the rest of the salt marsh. And through ramp pyrolysis oxidation and carbon isotopic analysis of the marsh surface soils, we observed that the main source of soil organic carbon came from salt marsh plant biomass, but varied in age, which has important implications in calculating marsh carbon burial. Finally, we saw that infilled ponds are making a valiant effort to recover elevation with almost double the accretion rate of the surrounding salt marsh. And so by incorporating our results from the field into an integrated salt marsh evolution model, which you'll learn more about from Julio, we hope to translate our findings into a decision support tool that can be implemented by resource managers like you to support restoration decisions and strategies on a larger scale. Thanks.